Welcome everyone. I am Jyotsna Singh from Indian Institute of Technology, Roorkee. Today, we are going to discuss about Hall effects and its working principle. Ever wondered how a magnetic field can affect an electric current? It's not magic, it's physics. Welcome to the fascinating world of Hall effect. The Hall effect, named after physicist Edwin Hall, is a phenomena that was first observed in 1879. It's the creation of a voltage difference known as the Hall voltage on the opposite side of a thin sheet of conducting or semiconducting materials through which an electric current is flowing. This voltage difference is created when the material is placed within a magnetic field perpendicular to the direction of the current. But how does this work? Picture this. When an electric current passes through the material, it consists of charged particles moving along. These particles, due to the magnetic field, experience a force, the Lorentz force, that deflects them to one side of the material. This deflection creates an axis of charge on one side and a deficit on the other, creating the Hall voltage. Now, the magnitude of this voltage depends on few factors: the strength of the magnetic field, the current, the thickness of the material, and the properties of the material known as Hall coefficient. This is where the fun begins. To find the Hall coefficient, we need to conduct a simple experiment. First, measure the Hall voltage with a voltmeter. Next, calculate the current flowing through the material and measure the strength of the magnetic field. Finally, measure the thickness of the material. With all these values in hand, the Hall coefficient, typically denoted by the symbol R, can be calculated using the formula Hall voltage divided by the product of the magnetic field strength, the current, and the thickness of the material. The Hall coefficient is a crucial part of this equation. It provides insight into the nature of the charge carriers in the material, whether they're positive or negative, and their density. It's interesting to note here that the Hall coefficient will have a positive value for materials with the positive charge carriers like p-type semiconductors, and a negative value for material with negative charge carriers for n-type semiconductors. But what about metals? You may ask. Well, metals typically have a very small, often negligible Hall coefficient. This is because the number of charge carriers in metal is so large that the effect of magnetic field on the motion of these carriers is minimal. Now, this is the setup of the experiment. On the left hand side, you can see the Gauss probe, and in the middle, you can see that it is attached to the Gauss meter. On the right side, we have a setup to generate the magnetic field, which varies as the constant power supply changes. We are using N-type germanium sample, and as you can see on the other side, we'll be supplying current source between the horizontal contacts, and we'll measure the Hall voltage between the vertical contacts. We have to first calibrate the amount of current applied and the magnetic field, because we cannot directly change the magnetic field. We are changing the current, and that is changing the magnetic field. So first we need to get this relation between the constant current applied and the magnetic field. So the Gauss probe has been kept between the north and the south poles, and as I'm changing the current, the reading of the Gauss meter is changing. As I'm increasing the current, the magnetic field is also increasing. So the first reading that we have to take is between the constant current applied and the magnetic field generated. This is a sample table that we got. In the next step, we fix the current passing through the sample at 2.6 milliamperes, and then we change the constant current power supply, and which eventually changes the magnetic field. So now we are measuring how the change in the magnetic field would change the Hall voltage across the sample. Take the readings by changing the constant current power supply in the steps of zero point 0.5 amperes. Reverse the direction of the magnetic field and take all the readings again. Here is the sample data table that would be generated. Next, we'll fix the constant power supply at 0.5 amperes, which corresponds to 200 gauss, and then we'll vary the current flowing through the sample and measure the Hall voltage. The current to the sample and the voltage output has a linear relation, so as we increase the current, the voltage also increases. And this is the sample data table that was generated. We repeat the same process for p-type semiconductor sample, and we observe as we plot the graph using the data that the slope obtained is positive for p-type semiconductor and is negative for n-type semiconductor. So that's all about Hall effect and its coefficient and how the magnetic field affects the charge carriers carrying the current in a semiconductor. Thank you.